In this video, I'll demonstrate how to create a script which will command the Schulman Telescope to take images for us. The tool to use is called the ACP Planner. It's a free download from the Astronomer Control Panel website. You can find this program by navigating to the website. One way to do it is just to type ACP Planner Download in your favorite search engine in your web browser. Or you can type in the following address. Here it is on the screen. It's at the ACP website. Once you navigate to this page, you'll see this particular page that you'll type in your name and all the other information so that they have you on file, and they will email you a link that will allow you to download the planner software. Go ahead and install this small program, and you'll eventually find yourself at a screen that looks like this. So this is the tool that we're going to use to create a script. Let me show you what a script looks like so you can just appreciate what it is we're going to be creating, and then we'll go about doing it. Here is an example script. Each of these statements are called directives, the ones that have the numbers out to the side. These are the commands. It's like a computer language. And each of these tells the system what to do. So ACP controls everything in the observatory, from the telescope to the camera, the dome, and these commands tell the system how to perform its action to get the data. So you'll notice that specified here are filters and exposure times, that's what the interval is here, as well as the position of the object, right ascension and declination, and even the position angle of the instrument rotator. Also notice that there are more than one objects listed here in this particular script. So this is one object, and then there's another set of observations here, as well as a new, as it so happens, object here. So these are the kinds of commands that we are going to create for the observatory to do its thing. In order to do it, though, the planner here needs to know a few bits of information about the observatory. It needs to know the names of the filters, and it needs to know what kind of dome we have, how often we want to autofocus, lots of things like that. In order to input all of that, I will have sent you a file, and that file is the profile for the observatory. You just load that file into the ACP Planner. So you go to File and Load Observatory Profile. The profile name will be something like this, Schulman Telescope Profile. So you open it, and then it's loaded. It's in memory. You can look at what the values are by going under the Tools menu and look at the preferences. Here you'll see that the filters are named and they're in their appropriate slots for the particular instrument that we'll be using. It also specifies some of the overhead that deals with, how long does it take to download an image? How long does it take to switch a filter? How long does it take to autofocus? These overhead times also go into the calculation of what is the total amount of time it's necessary in order to collect data. There's also a few other special characteristics here. One is this value that says the maximum unguided exposure. In this case, it's set to 5 minutes, and that tells the system that all exposures that are less than 5 minutes will not be guided. They'll just be unguided. The Schulman Telescope performs exceptionally well, and for short exposures it's not necessary to have the overhead of finding a guide star. Just take an unguided exposure. In addition, the autofocus section here says, do you want to focus at the beginning of the plan? And the answer is almost always yes to that. And then how often do you want to do continual focus updates? In this case, 90 minutes is usually about right. So these are the features, these are the things that are set for the observatory profile. So you shouldn't need to touch it, but I just wanted to show you what it looks like. Now, in order to create an observation, that is to look at a particular object in the sky, you need to have, before you come here, 3 pieces of information. It's right ascension, declination, and the position angle if you're going to be doing guiding or composing the image in some specific way. So in order to do that, in a previous video I illustrated how, by using a field of view indicator, you can specify not only the composition of the field, but also you could identify particular guide stars that you would get this information about. So please review that video to learn how to get those numbers for the position of the center of the field of view, as well as the rotation angle, the position angle for guide stars. Once you're satisfied that you have those values, then you can come to ACP where you'll be able to input them. The easiest way to go about doing that is to right-click here in the target window, and we will just add a new target. Ignore this because that's a silly error. You shouldn't have that error. And you add a target to the plan. Now the way ACP works is you can add a target name, and this target name is really just a descriptor. It's what we're going to be calling the target. It doesn't know anything about that. We can look up a name that will be resolved during true runtime. That is, at the telescope, when ACP looks at the name, then it'll resolve it and say, okay, I know the coordinates. Alternatively, you can type in the coordinates here. So, let's say, for example, we were going to take a picture of the Whirlpool galaxy. So, I'm going to type Whirlpool here, and I'm going to misspell galaxy on purpose because this is just a name that I am giving the field. Now, as I say, if this is a common object, you can look up the object, search for the names here using the catalog. So you would go to Search Names, and here we're going to search for the true catalog name. In this case, it's M51. Now in ACP, note that I put a space here. Anytime you use ACP to search catalogs, you must put a space between the catalog name and its catalog number. So we would search, and it comes up with it. Now, if that just means that it searched all of the names that ACP understands, and it says, I know one that's called M51. Had I put in here NGC 246, you'll find that it comes up with more entries, because there are many NGC 246s, followed by the string that has 1, 2, 3, 4, 5, and so on. But for M51, that was unique. And we go, OK. Having done that, the automatic dithering here is an option that does interest us whenever we add a target. This means that it'll shift the telescope a little bit between each image, and that will make for a better result when you combine the data later. So all of this is good. I've actually specified the minimum altitude. This is not within your realm, so don't worry about that. This is all you would do. You put in the target name that you want to call it. In this case, I guess because I looked it up, it's now going to call it M51. And you can also just, as I say, specify coordinates. Now, if I specified a coordinate, and this is going to be the center of the field of view, it doesn't need to be the actual, centered on the target itself. So it's really the center of the field of view. That's what we would put in here, the numbers. Now the values I don't know off the top of my head. And we would also specify a rotator angle so that we can accommodate a guide star. That's how that would look. These are the fields that you would put in the three numbers, right ascension declination and the imager rotator angle. But we liked this version just for the moment. This is going to assume for us that kind of north is up and we're not going to guide. We're just going to take an unguided exposure of M51. And we'll force that because we'll specify here in a moment the exposure time. We'll force that to happen. The next thing to do is basically program what kind of exposures we want to take. Let's pretend we were interested in generating the color data for M51, and we were going to do relatively short exposures, that is unguided. So we might specify the red filter, the green filter, and the blue filter. This would be the color data. And let's say we wanted to do, the 5-minute exposure. So this is the 300 seconds in each filter. And the binning, typically, when you do these kind of data, you would do it binned 2 by 2. The number here is going to specify how many of these we want to take. And since this is already a triad of filters, I'd like to demonstrate the difference between these two ways or these two methods of doing it. I could either specify like maybe an hour, so no, not an hour, half hour, 6 exposures in each filter, and when it runs this program, it will do the first red, the second red, the third red, and so on. It'll do all the reds first, and then all the greens, and then all the blues. So that's one way to go about doing this. The other way is to specify the number to be 1, and then do it 6 times. This will go through and do the red filter first, the green filter, and then the blue, and it'll do it again 6 times. Red, green, blue, which is a different way to acquire the data. That's typically the way that I would go about doing it. But just know you can run the loop in 2 different methods. So if I wanted to do all of the luminance data first or something like that, I can do that and then specify it to loop around in the RGB data here. Now, if I like this, and this is not critical or necessary, you don't need to have a preset, but if you plan on using the Schulman Telescope often, you could create one just so you have it in your back pocket, or you wanted just to load this information again. All you need to do is save what we've typed in here as a preset. And we'll call it some different name. We'll rename this. I'm going to call this unguided, since this will be an example of unguided RGB information. I really have to turn off these tooltips. Okay, so we've got the unguided RGB. That's the name of this thing. Hit update here. Close. And now, we can select that, and we'll create another preset, say for luminance, which was going to be a little bit different than this, the unguided RGB. Now, the final thing to do is to actually create the script. I mean, we've done it. We've programmed everything we need to know here. So to create the script, you go File, and you save this plan under some name. But what's going to happen, you would think that's all you had to do, is you're going to get an error here. It says, unsaved image set will be lost. Are you sure you want to create a new plan now? Answer no to click Update to save changes. That word, update, is the critical one. I'm going to say no. What I want to do before I do anything else is hit this update button, because without doing so, the planner doesn't know how long it takes to do everything. It needs to actually calculate that before it can write this little script for us. So if you ever try to save it and you get this error box, it's not really an error, but it's kind of a warning. Say no, and be sure to press the update button. It is so easy to forget to do that. When you press the update button, you'll get a wonderfully red text here that indicates the total amount of time that you've programmed to do this. And you'll notice the total amount of time exceeds what we actually did, 90 minutes here, because it's also folding in all of the overhead time for everything else that was necessary. Now, if we go to save the plan, we can save it in some name. Now, you'll see I have some plans there, so I'm going to call this M51, and we'll call it unguided TXT. I've saved the plan, and I'm going to put this as my first unguided image. And what we get is the plan. Here it is. This is what we've programmed it to do. Now, I'd like to just step through and show you what's in here. The little semicolons are comments, so they're nice. They give us information, but they're not actually commands. What this says is going to happen is it'll autofocus first, and then it'll also count to every 90 minutes and then do another autofocus routine, which is invoking focus max on the Schulman observatory system. And in this case, we have one target here. It's M51. It will dither the telescope automatically. That's what the automatic dithering is. However, at the moment, the automatic dither, that if you do nothing else here, is fairly small. So here is one thing that you could help me change, although I'll do it for you if you submit it, if you forget to do it. But put in the number 5 here for the dithering magnitude. That's how many pixels, or at least in terms of a magnitude, how far it's going to shift from image to image. And 5, not the automatic default setting, but 5 is going to be the number that we actually want there. The repeat here, as you know, the repeat is going to do this outer loop. So it's going to repeat everything interior to it. And it'll go through and take the red, green, and blue, and then it'll repeat and do another red, green, blue. The intervals are 300 seconds apiece. You'll notice there are commas separating them. And the binning for each one of these is 2. The position angle we did not specify, so it is north at the top, which is a position angle of 0. And this is an interesting line here. If we had specified coordinates, like you saw in this previous plan I brought up, you know, an object will have coordinates that correspond not to the object itself, but instead to the center of the field of view. However, in this case, we decided we were just going to put in the object name and just have it at runtime look up the coordinates of this object. And that is going to center directly, exactly on the object. So M51 here, when we run this plan through ACP, ACP will understand, oh, I know the coordinates of M51, and that's where it'll point the telescope. That's it. You will have created your first plan at this point, and you could upload this, which is going to be one more tutorial that I'll have to show you. You will upload this to the observatory, this text file, and then press go, and it'll take the picture. Now for a guided exposure, like I showed a moment ago, we would input the 3 values, the right ascension, declination, and position angle, of the center of the field of view. Let me just go ahead and do that. It'll allude back to the previous tutorial, but it'll also demonstrate how we could put multiple targets in this plan if we wanted to. So, to do that, I'm going to bring up my Aladdin Sky Atlas, and let's say, and I'm just going to use what I did in the previous video, let's say we wanted to do that NGC 2798. So I'm going to delete all of these planes. We'll type in a new object up here, which is NGC 2798. And there it is yet again. We can load our field of view indicator. And again, just go to the Schulman, which is impressive that it's in the list, Schulman Telescope. And as we did before, the guide star that we determined was going to be reasonable were 2 that were down here. So I know I need to rotate this field of view indicator down there, and I believe the value was like 117. This is just my memory. You go to Properties, and you change this roll angle to 117 degrees. There it is. It did shift, or rotate. And now we do need to translate the field of view indicator to accommodate those stars, or that bright star anyway. So I now have it in the box here, and I still have my object in the field of view. Now if I go to the Properties, and we look at those values, these are the values that I'm going to take and put into the ACP planner. What I don't know if I can do, let's see, how can I do this, is I'm going to bring up ACP planner here. Good. And I'm going to try to keep them both on the screen at the same time, so I can just type them in. And what we'll do is we'll create add a new target. The new target name is going to be NGC 2798. And this time we specify these coordinates, 0, 9, 17, and then 15.2, as well as a declination of plus 41, 57, 20.6. And then the rotator angle, 117. That's it. So we still have the automatic dithering, we have the name, everything's good there. And it adds the new target for us. Now I'm going to, let's say that we were interested in programming to do luminance only for this data set, and that's going to require the guiding because we're going to do long exposures. So we will specify the filter to be clear. The number of them, we could either do it as a repeat or a count here. It doesn't matter because it's just going to be one filter. So we'll put, I don't know, we'll do 12. That's a lot. We'll do 12, it's many hours here, 15-minute exposures and unbinned. And this is really the benefit of using the telescope in the real-time mode, is that we can use it to its full, the full ability, full power. I'll update so that we get the total amount of time, 3 hours. And if we want to, we can save this as a new preset. This might be, let's call it a different name. This might be luminance guided or something like that. And that way I can now load this one as opposed to the other one. Having done that, we now have 2 targets, and it'll go to 2 different things. So all I need to do is save. I did update, so I should be able to save this plan. And I'm going to give this a different name. It's going to be called multiple. Yeah, I've already done this before. Multiple targets as an example. Save. Do I want to overwrite it? Sure. And this is my first multiple target plan. You can type whatever you want there. It's just fun. Here's what the plan looks like, and again you'll see that now it has written in here both objects. Notice that the repeat here is 1 and the count is 12, whereas the repeat here is 6 and the count is 1 for each of the filters. Also notice that there aren't commas anywhere here because there's just a single filter. So that's what the script looks like. It does all of this automatically. To program the Schulman Telescope, once you kind of get this, takes all of about 30 seconds. Now, as a final bit here, let's say that we now have this programmed here to do the luminance, but we wanted to do also the color data. So we could again add a new target, but this one will save a little bit differently. We'll give it a different name, 2798, and we're going to call it RGB for the colors. We'll still type in these values. I could have copied and pasted, but 41, 57, 20. By the way, I could have copied and pasted right from the text file. I don't even need to use the planner at this point. You can edit the text file itself. It is synonymous. It's just nice that this tool does these things for you. But if you want to use this tool to do it, so you won't have any syntax errors, that's obviously the safest way. The rotator angle we know is 117. We go OK. So now RGB, of course, we want to program the RGB, and this time it's going to be a variation of our unguided RGB. So I can apply the preset here, but then I can, of course, change it. And I'm going to make these 600 seconds. So ACP will know to find a guide star automatically because we're specifying a time more than 5 minutes. The bidding, though, will keep the same. And we'll keep it with this rotating through the filters as part of the triad of red, green, blue, maybe repeat, I don't know, 6 times. So we update. Now we have a plan which has all of this stuff going on. This may not be something we can complete in a single night, but it is all there for us. So we'll save our plan, and we can just overwrite our previous multiple plan, multiple targets. And I'll say final plan. Final plan. And now we have everything that we wanted to do for an observing night at the Schulman Telescope atop Mount Lemmon, 9,000 feet up. You have all the targets in place, and it'll take color data of M51, then it'll move over to some interacting galaxies, do the luminance, followed by color. So I hope that you see the benefit and the power of using this tool to create a script for programming the observatory to do everything. And I think once you give it a shot, at least once, you'll see that it all kind of falls into place. It's very simple. And you'll just send this file to me. Or you can upload it yourself, by the way, at runtime. So I don't even need to be part of this. You can do this on your own. You may want to send it to me, though, just to make sure that there isn't going to be an error with regards to something else subtle that might be going on. So thanks for listening, and I look forward to having you use the telescope and gather great data.